I'm so happy to be here. I can't tell you how much agony we went through trying to save this MEG. And I have to say that Ramesh came through in a way that showed leadership and vision that we didn't find in medical school, I'm sorry to say. I'm not talking about the chairs. I'm talking about the money people. And this is a fantastic facility. And we have the best MEG room and instrument in the world. And we have the best group of people working on it. So I think we could use more people coming and using it, especially from the upper campus. And I really hope we do have that. And one point I'm going to make in my talk, I don't know, it's kind of strange here, but we'll make it work, is that MEG is complicated, right? It's complicated. It's kind of something that is is harder to think about and to do than fMRI. fMRI, like you kind of turn the crank and you get spots. And gee, spots are great. Okay, this spot and this spot and this spot is, passion or, attention or memory, language, whatever it is. And MEG is more physiology. And that basically is what I am. I'm a neurophysiologist. And so it's evolving in time. And it's complicated because we don't understand the physiology of the brain. We understand dots, and spots. So, we can relate that to cognitive whatever. But if you want to talk with anybody in the MEG Center, please get in touch with us when you want to design an experiment, because designing an experiment with MEG is a little harder than with fMRI, and analyzing it's harder, thinking about it's harder, deciding what's a good experiment is harder. So please feel free to talk with us and just lower your activation energy. Okay, can we start? And Bob too, it's great to see Bob. Is Bob still here? Anyway, we work together in the academic senate. So I'll talk. All right. So that's me. That's my email. Use it. So here's this little cartoon, and it helps you think about what we're looking at. This is a synapse. It comes up here to a neuron, and it makes a hole in the membrane. That's what they do, when you activate a synapse, and some positive thing goes in, positive charge, positive ion, and because it's a long tube, the apical dendrites, it flows down, and this intracellular flow of current is the MEG, and you record it directly. It passes directly out to your sensors. So you are recording instantaneously the currents entering the apical dendrites of the pyramidal cells in the brain you're recording from. This is amazing. With fMRI, you get like some sort of delayed by 2 to 10 seconds hemodynamic response, which is great. It's revolutionary. This, you're seeing real time the synaptic activity of the brain, of the cortex. And of course, you have this return current that happens outside, and that generates the EEG. Well, so the problem is that you've got this big conducting thing here, and so the current is flowing all directions, and anything you want to record, it has to, gets distributed throughout this bag of water, and that smears everything, especially because you have the skull in between. So I'll show you the effect of that. Okay, but first I want to talk about some of the problems, because I always, being a scientist and you being scientists, you want to hear about them. So there's antecedent processes that tell you, oh, something's got to happen. There's some trigger, there's some coactivated areas. We don't see things like this because the currents are canceling, right? And we don't see something like this. Let's say we're on two different sides of a sulcus and they are coactive, they're going to cancel each other. So we just see some small percentage of the activity. And we've calculated this, and you see, you know, like much less than 1% of what's going on in the brain with MEG, which is good because there's so much going on. If you are 99% blind, you can figure out what you're seeing in the other 1%. The problem with EEG is not that it's not a great signal. It's just that everything's so smeared, you see everything, so you can't make any sense of it. MEG, you can understand things because you're only seeing a little bit of what's going on. So this is, not everyone will agree with this figure, but I believe it's true. This is the lead field. What's a lead field? Well, this is like you have the maximum dipole that's responding to, and you're showing the percent of that you're recording, that you're sensitive to with a single gradiometer. And that's amazing. So you can just take directly the signal from the MEG in a gradiometer and pretty much know where it's coming from. This is the corresponding one for a monopolar EEG. it's all over the place. So that's a problem. See, so that's the power of MEG. And the problem, though, in source localization is that it is impossible to know for sure where things are coming from. So you have to be clever, like Ming Xuang is, in figuring it out. And this is an example where we took two dipoles, we put them in the primary visual cortex on one side and the other, and this is on the left side, this on the right side. You add them together and you get this. You get these four bullseyes. So you could say, well, it's either coming from here and here, or from here and here. You know, it's ambiguous. So there's this inherent ambiguity in the inverse solution. I'm going to show you various ways to reduce that ambiguity. And one way is to insist, I don't know, look, I'm pointing it over this way. How is that happening? Okay, anyway, this is, you insist that the dipoles you're recording are in the cortical surface. So that's why you want to get a structural MRI to use with the MEG. And that way you can get an anatomically constrained MEG. So this is a Stroop task. This is the work of Ksenia Marinkovic. And a Stroop task is where you have this oh shit response. You set something up so that you are going to respond in a certain way every time, and then you put in a ringer in there, and the person makes a response, okay? The wrong response. And that is the basic thing for a Stroop test. And we know that this part of the brain, the anterior cingulate, is just really very important for that, and this is the MEG activation for that. And sensitive to conflict, she said. But here's a takeaway. This is a legal level of alcohol, and you don't notice when that kid is running across the street in front of you. Okay, so don't drive. Your ACC is not getting activated. You can also do things in frequency domain. This is the co-oscillations of phase locking in, I think it's theta, between the anterior cingulate and the lateral prefrontal cortex, because the anterior cingulate's detecting when you like make a mistake, but it's got to get your what does it do then? It's got to get the rest of the brain engaged in paying better attention. Okay. So alcohol again wipes it out. So she provided these movies, and this is something you can do with Meg, is make movies. Oops. I am sorry, it's kind of too advanced for me to get the movies. Did somebody do that? Somebody did something. Is there an AV person here? Great. Yeah, push. You can do it on the other side too. Great. So people are hearing words or reading words, and this is you could push them again just for fun. So this is a minimum norm solution, noise normalized minimum norm solution that Anders Dale developed. And it shows in a size judgment task, the activation to visual and auditory words. And you can see it starting back there in the visual cortex and here in the auditory, and then going to common areas concerned with language. And this is the picture of the N400, which is a marker for understanding of things, understanding of words in this case. And you see it goes to the same place for auditory words atop and visual words on the bottom. And, we've done a lot of intracranial recordings, and these localizations are correct. So here's a wonderful study that I've had the great pleasure to do with Rachel Mayberry and her team. I don't know if Rachel's here today. Yay, and her team. And Rachel has done amazing work on language acquisition. She studies people who acquire language at various ages. And that happens because they're deaf. And some people who are deaf don't get exposed to language until they're older, sometimes even in their teens, for various socioeconomic and social reasons. And here is two people that had got language in their teens, early teens. And here is a native signer, a person who learned sign language from birth. And you see here, this is like what we were seeing before for MEG, for the activation to words, same sort of task, but now we're doing it with a picture and a sign. So again, we're looking at the American Sign Language, and the picture either matches a sign or not. And Shauna and Carlos have activation. They can learn to do this, but it's here in the right parietal lobe. It's not here in the left temporal. And this is possible with MEG because it's so easy it's so non-invasive. I mean, fMRI is non-invasive, but it's loud and kind of scary. And MEG is totally silent and totally non-invasive, totally harmless. So this is just an example of one of many studies with Rachel that are really incredible. So I think one other thing you can do, and this was with Anders Dale again, is you can use fMRI in the same task to focus. Here is without fMRI, just using the cortical surface to try to understand where the activity is coming from. And here's where you have fMRI in the same person, and you can use the fMRI to help focus the MEG response at different latencies. Another thing we're working on is we have 300 patients and thousands of locations. And what we're doing is trying to understand the correlation structure of the activity in the brain. And here are, the thing is, distributed sources are really hard to figure out because your solution is going to depend upon your assumptions. One of the biggest assumption is what is the correlation structure of the activity in your brain? And I won't go into all the details, but this is the right correlation structure for what we're looking at. And you can see it's quite different from the other solutions. But we know that this is the right correlation structure. All right. So the conclusions. MEG is a direct instantaneous measure of intracellular currents in cortical pyramidal cells. Easier to localize. The transmembrane currents are the fundamental currency of neural processing, and is completely non-invasive and well-tolerated. Source localization is inherently uncertain and requires assumptions of variable reliability. I have to say, for the sorts of things that, most of the things that Ming Shuang and Roland were showing were focal sources. And for that, it's really, the solution's fine. Your assumption is that it's focal, and MEG is extremely reliable and powerful there. The problem is with distributed sources, I'm sure you agree, where you have to make assumptions. And so I think this is something that's an area of research, and engineers would be welcome. So I guess adding information with MRI is good, and intracranial recording can validate. All right, that's it. Thank you very much.